In this next section, we're going to look at nomenclature of alkenes, or in other words, naming. And if you learned your alkane nomenclature really well, then learning alkene nomenclature should seem relatively easy. There'll be one new thing we really have to learn, but other than that, it just kind of builds a little bit, but is very similar to the naming rules you've already seen before. And that's how it should be throughout this class. Every time we introduce a new functional group and we learn the nomenclature part, that should be like your low-hanging fruit. That should be the easy thing for you. Because if you know the nomenclature basics, you can name almost anything in organic chemistry with just a few modifications here and there. If you recall, when we learned alkanes, for an alkane, our suffix was ane. And so all of our molecules up until now have ended in ane. For alkenes, the suffix is changed to ene. We talked about that the hybridization was sp2, the geometry was trigonal planar, the bond angles were 120 degrees, and we had a double bond which represented a sigma plus a pi bond. So that's just a little review. The general formula for alkanes was CnH2n plus 2. Something that we're going to talk about at the end of this chapter in the last part is called degrees of unsaturation. So alkanes are considered fully saturated. And if you've heard of saturated fats, that's kind of the same thing. They have the maximum number of hydrogens that the carbons can hold around them in the chain. And so they have no degrees of unsaturation, 0 essentially, because they're fully saturated. Versus alkenes are unsaturated. And later we'll learn how to calculate their degree of unsaturation. But I'm bringing this up now because if you compare the general formula for an alkene with that of an alkane, the general formula for any alkene is CnH2n. We lose that plus 2 part. So an alkene is going to have 2 less hydrogens than its corresponding alkane. So, for example, for butane, which we would have previously talked about, the formula would be C4, and then we would have 2 times 4 plus 2, we'd have H10. That would be our formula for butane. For a molecule called butene, which would be the alkene version of this, we would have C4, and then H, it'd be just 2 times 4, 8. So notice there's 2 less hydrogens in the alkene, and that's due to the presence of that double bond. But you can use the general formula to quickly calculate, for any general alkene, what its molecular formula should be. Okay, so let's go through some basic nomenclature rules. And then after we go through the basics, we'll add on the new part after. So first you want to identify the longest continuous carbon chain. And what's new here is now it has to contain the carbon-carbon double bond. Last time we were just looking for the longest chain when we talked about alkanes. But if we're going to name an alkene, now this functional group becomes the priority. So we have to include it in our numbering of the longest carbon chain. And that's going to be our parent. So recall that your parent is what you place at the end of the name. Remember, you can follow through with kinks, bends, and turns. So when numbering, for example, if we start on the left, you might think you want to go 1, 2, 3, 4, 5, 6, 7. You have 7 carbons in that chain, that would be hept. But I did not include the double bond in my numbering, so this is not going to be correct. Instead, what I want to do is number through the double bond. So 1, 2, 3, 4, 5, 6. Even though I have less carbons in my overall chain, this is still my correct parent chain because I numbered through the double bond. I contained the double bond in my numbering. So this would be my correct numbering there. So I have 6 carbons in that parent chain. This would be hexene. Notice that I ended the suffix with ene. That's going to be our suffix this whole chapter. Second rule, begin numbering the chain at the end nearest the double bond. The double bond represents the alkene functional group and must have the lowest number possible. So right now, we are not mixing functional groups together. We are just focusing on alkenes. And so that is your priority. And you always give your highest priority functional group the lowest number. So when you have a mixture of a bunch of functional groups, you have to use a priority list to figure out who is the highest. Right now, we know that the alkene is the highest. So if I, on the left, was to start numbering from here on the left-hand side of the molecule, I have 7 carbons in my chain, and my alkene is in between carbons 4 and 5. But if I go over to the right and I number from the right, 1, 2, 3, 4, 5, 6, 7, still 7 carbons in my chain, but now my alkene is in between carbons 3 and 4. And we always look at the carbon where it starts. So when I numbered on the right, my alkene got a lower number. And that's what we want. We want it to have the lowest number possible. So this is the correct numbering, and on the left would represent the incorrect numbering. We also indicate the position where the double bond is at, because we know that this has 7 carbons in it, so this would be hept for the 7, and then ene for the alkene, but we wouldn't know where the double bond is located at. Is it in between 1 and 2, 2 and 3, 3 and 4? And so we take that lowest number and we write it out in front. So this isn't the full name for all of the molecules yet, but for the simple one like this, where it's just a double bond, this would be called 3-heptene. That 3 out front tells us the position of the ene, or of the alkene, the double bond. So rule number 3 is actually what we just talked about. The double bond lives between 2 carbons on the chain, and so we have to identify the position that it's at. We use the lower number, and we put that out in front of the parent chain, the parent name. So let's put this whole one together and name the complete molecule in this example then. So we're going to start numbering on the right, because we want to give our double bond the lowest number possible. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9. And if it helps you, you can write down known ene at the top first and make a little list before you try to put it together in the complete name. Next, make a note of what your position of your double bond is. It's in between 3 and 4. So we use the lower number. This is going to be 3 nonene. And then we want to identify what our substituents are. At position number 4, we have a methyl group, so we have 4-methyl. At position number 7, we have a bromo, and 8, we have a chloro. Recall now that when you put the full name together, this is just like alkanes, you list the substituents out front, in front of the parent, and you put them in ABC order. So we're first going to go with bromo, then chloro, then methyl. All those will go out in front of our 3 nonene. So our complete name then is going to be 7-bromo, 8-chloro, 4-methyl, hyphen, 3-nonene. So we use that 3 out front just like we would any other substituent. It's a number, so we separate numbers with hyphens. Numbers and letters with hyphens, I mean to say. So just like 7 out front tells you the position of where bromo's at, or 8 tells you the position of where chloro's at, 3 tells you the position of where the double bond is at, the ene part is at. Next, if you run into a situation where the double bond, the alkene, is equidistant from either end, then you're going to begin numbering at the end nearer the first substituent. So this is actually something that we previously saw when we were deciding on our numbering. We used giving the lowest numbers possible to our substituents as a way of breaking a tie when we needed to. And then if we had to, we moved on to ABC order. You usually won't need to do that because the alkene position will kind of have to be the lowest, and so you won't usually have to move to that many places of breaking a tie. But if you have to, like we do here, so if we go from the left, 1, 2, 3, 4, 5, 6, 7, 8. Here, numbering from the left, our double bond is in between positions 4 and 5. And if we start on the right, now we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so our double bond still pops up in between position 4 and 5. So now we have to break that tie. And to break that tie, we look at, well, on the left-hand side, we did not come to our first substituent until number 3 at bromo. But on the right-hand side over here, our first substituent popped up on number 2 with chloro. So number 2 is lower than 3, so that's going to be the one that we use for our numbering. That's nearer the first substituent. So the one on the left would be incorrect. We would follow the numbering pattern on the right. So the full name of this molecule then is going to be 6-bromo, 2-chloro. What's the position of our double bond? It lives between 4 and 5. We indicate that by using the lower number, which is 4. We had 8 carbons in our chain, so that's oct. And then it's an alkene, so ENE, octene. Do you remember back in general chemistry when you learned how to name molecules? So molecules were two nonmetals together, and we used Greek prefixes to indicate how many of the metal there was present in that molecule because they didn't form ions, so we couldn't use, knowledge of, oh, this forms a +2 or something. Molecules, we had to use either, stuff like mono or di or tri or tetra or penta, hexa, hepta. Those were all Greek prefixes that we used to indicate the number of atoms in them. Those actually come back here in a situation like this where we have multiple double bonds in a molecule. So multiple double bonds are named using the appropriate Greek prefix. So for example, if you have 2 double bonds, those are called dienes. So di means 2. 3 double bonds in a molecule, those are called trienes. Tri means 3. If you had 4, they'd be tetraenes. We kind of dropped the A because of 2 vowels there. You shouldn't really need anything more than that. So now let's do these 2 examples and put everything we've learned together so far. So starting with the one on the left, we want to start numbering so that our double bonds get the lowest number possible. And we're going to start numbering from the left-hand side for that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got 10 carbons in our chain here. And so we're going to have in ABC order, we're going to have 7 bromo, 8 chloro. And then now we want to indicate the positions of both of our double bonds. We want to indicate both of them. So 3 and 4 is our first one. 6 and 7 is our second. So 3 and then 6. So just like when we had, for example, if we had 2 bromo groups, we could say 2,2-dibromo or 2,3-dibromo. We'd indicate the 2 positions that those bromo groups live on, and then we threw the Greek prefix di out front. It's no different for an alkene. So for this one, we would say 3, 6. But first, we list the number of carbons in the chain. So we say dec, and then we add in our new part here, diene. So this diene part is our new suffix because we have 2 double bonds. And the numbers that you have out front should match. So I have 2 numbers and I have a diene. That's because I have 2 double bonds I have to indicate the positions of. Let's try the one on the right-hand side here. So the one on the right-hand side, we're also going to number starting on the left. So 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons in our parent chain. And 11, you might not recall this, but it's un deca. So un deca is 11, deca is 10. And our substituents, we've got an isopropyl at position 7, and we have an isopropyl at position 8. Oh, no, sorry, ethyl. Ethyl at position 7 and ethyl at position 8. Isopropyl is over here on position 3. So first, let's put our substituents in alphabetical order. So we're going to have 7, 8 diethyl. So it still goes by E, even though we put a di out front. We don't use the di for our alphabetical order. Hyphen, we have 3 isopropyl. Oh, I'm forgetting one other thing. I'm forgetting the fluoro group right here. So at position 6, we have a fluoro group. So actually, that's going to come after E alphabetically. So 6 fluoro, it's FLUORO. Next, finally, 3 isopropyl. And isopropyl, remember, goes by I. It's not hyphenated, so it goes by I for alphabetical order. All right, now we're to the new part here. Our double bonds, we have to indicate their positions. So looking at our molecule, we've got a double bond between position 2 and 3. We've got a double bond between position 4 and 5. So 2 is one location, 4 is the other location. So we're going to have 2, 4. And then we've got un, dec, a. That was our 11 carbons in the parent chain. And then our ending is going to be diene. So 2 and 4 for our diene. So we previously saw cis and trans can be used for stereoisomers, where we were talking about if two groups coming off of a double bond are on the same side, like this, for example, or if they were on opposite sides, like this. So this would be trans, this would be cis. And in this case, it's really easy to know what I'm talking about because the two groups are the same. So I'm comparing two fluoro groups to one another. So I can say, oh yeah, those fluoro groups are on opposite sides, or those fluoro groups are on the same side. But if I had a bunch of different groups and I had more than two groups coming off, I mean, we saw that alkenes can be tri-substituted or tetra-substituted, then we need something a little bit more, rule-oriented in order for us to be able to determine what's on what side and how do we name that, and then how do we take a name and put it into a structure that everyone can arrive at that same structure. And so chemists can communicate and know they're talking about the same molecule, especially since those stereoisomers have different physical properties. So next we're going to learn some rules that you're going to add to your naming of alkenes. So really, we did not actually fully name all of those alkene examples we did. We did like the really hard part of it. We did most of the work, but now there's going to be this new part of it where we have to add on to indicate what stereoisomer we are talking about, and it's not going to be with cis and trans. So in order to complete our nomenclature rules, we're going to learn something known as the EZ system. So when we name alkenes, we want to use a set of rules in order to determine what groups are considered the highest priority groups. And then we decide if the high priority groups are on the same side of the double bond, so both up or both down, or are they on opposite sides of the double bond if we draw an imaginary line through it. So the E stereoisomer stands for antigen, and these are Greek words, that's where they come from. And that's where the high priority groups are on opposite sides or on opposite faces of the double bond. And the Z stereoisomer, Zusammen, stands for the Z version of it, and that's where the high priority groups are on the same side. So on the left-hand side, notice how we have our double bond, or alkene, and imagine if we were to draw a line down it and split it in half. If we figure out what the highest priority groups are coming off of the double bond, and we say that the high priority group is pointed up on this one, coming off of this side, and on the other side of the double bond, the high priority group is also pointed up. So we have it pointed up here, and we have it pointed up here. Then those two groups are on the same side of the double bond. So that would represent the Z isomer. And opposite to that, imagine if we break the double bond here in half, and we haven't talked about how you know what the high priority group is yet, but if we figure out the high priority group, and then this one on this side of the double bond is pointed up, and this one on this side of the double bond is pointed down, now you can see that those two groups are on opposite sides of one another, and that's called the E stereoisomer. So E was similar to trans orientation, and Z is similar to cis orientation for when you use just the simple cis and trans. Those would be their counterparts. So cis is Z, trans is E. But now we have more complicated molecules, so we need a system to figure out, well, who is the high priority group? Who is the LP, which stands for, in this picture, low priority group. So what we're going to follow is something called the Kahn, Pre, Log, Ingold rules. And it sounds scary, but those are just three chemists' last names who came up with this method for determining priority. And it's used for all kinds of things, not just for E and Z. We'll see it later when we learn other stereochemistries as well. And what these CPI rules say is that we use the atomic number in order to figure out who is the higher priority group and who is the lower one. So atomic number, remember you can read that right off the periodic table. So you're going to want to have one of those out or kind of know the general gist of where the elements are. We don't look at atomic mass, so we're looking at exactly the number of protons, the atomic number. So we just said that priority is based upon atomic number, and that means that the higher the atomic number is, the higher the priority. And so that's how we determine off of one side who's the high priority group, who's the low priority group. And then we do the same thing for the other side of the double bond. We use atomic number and we figure out who's the high priority group, who's the low priority group. So in the upper right corner, I just did a little brief part of the periodic table with some common groups that you see a lot in organic chemistry. So bromo has a higher atomic number than chloro, has a higher atomic number than fluoro, higher than oxygen, higher atomic number than nitrogen, which is higher than carbon, which is higher than hydrogen. So hydrogen, when you see that, you want to think in your head low priority. Hydrogen is atomic number 1, so it's the lowest priority that you can have. So pretty much anything else is going to be a higher priority than hydrogen if we had it coming off. So let's look at this first example and give the complete full name, now adding on our easy nomenclature rules. And we'll start out simple, and then we'll kind of try a couple more later where we build upon this. So the first things we want to do is still number correctly. And if we number from our left-hand side, we're going to go 1, 2, 3. Our first substituent pops up at 3, whether we number from the left or right. And actually our double bond pops up at 3, whether we number for the left or right. So you might recall that when you want to break another tie, you would move to alphabetical order. So bromo is lower ABC order than chloro. So that's why I'm going to number from the left. So then I would go 4, 5, 6. And we can do everything that we learned so far. We're going to have 3 bromo, 4 chloro, and then our double bond is at position number 3. We have 6 carbons, so it's going to be hex, 3-hexene. So now let's figure out our priority groups. So first imagine you break this double bond and you have 2 sides. You have a left side and you have a right side here. So coming off of the left-hand side, off of this carbon, we're just looking at the left-hand side right now of our imaginary green line that's running through our molecule. So off of the carbon number 3 on our left-hand side, we want to work our way away from that yellow dot that I drew. We want to work our way away from the double bond. So we don't look at that carbon that I have circled where that dot is. So we move away. When we move away, one atom at a time, we say what it is. When I move up here, the first thing I come to is a carbon. When I move down from the dot, the first thing I come to is a bromo group. So my tie I have to break is between carbon and between bromo. So between carbon versus bromo, bromo has the higher atomic number. So that means that this is going to be my high priority group, is the bromo. That would make this whole thing, this whole ethyl group, my low priority group, which I don't really need to circle that. I'm just comparing high priority groups. So then we do the same thing over on the right-hand side. So now we're working on the right-hand side of our imaginary green line. And coming off of this position right here, so I'm not counting that one because both sides have that same carbon-carbon double bond. So I look at each atom one at a time coming off of that spot. If I go up from there, I'm going to come to a chloro group first. That's directly bonded to that purple dot. And if I go down from that purple dot, what I'm going to come to is a carbon group right here. So now I have a war on the right-hand side of chloro versus carbon. Who has the higher atomic number? It's going to be the chloro group. So this is my high priority group, and then this ethyl group right down here becomes my low priority group. Notice it's not just the carbon atom that's low priority, it's the whole group that the carbon atom's on. But I look at it one at a time, and the carbon is what lost the tie. So it's that whole ethyl group that gets designated low priority. So now what this tells me then, since I've identified my two high priority groups, one here, one here, are they on the same side of the double bond, or are they on opposite sides of the double bond? One is pointed up, one is pointed down. So they are on opposite sides of the double bond. And we said that opposite sides was called E. So how we finish naming this molecule, now that we determined that it's E, is we put the stereochemistry out front. So out front in parentheses, and then a hyphen in between your molecule, you put 3E in there. The 3 matches. It's 3 here, 3 out front, it's 3 here. That's because that's where the double bond is. So the 3 just tells us the stereochemistry. Some books or people might take a shortcut and they don't put the number out front. If there's just one double bond, they might get lazy, but you are technically supposed to list the number out in front of the stereochemistry, because once you have multiple double bonds, you would have to differentiate them. So those two numbers match there. So this is our stereochemistry right here, that 3E. So that tells the reader that when we draw this molecule, if we were working from a name, that I got to put my high priority groups on opposite sides. And because we followed rules to determine what our high priority groups were, everyone knows and can draw the exact same molecule. So in our last example, we found a difference right away. On the first two atoms that we moved away from the double bond we had a difference between them. Sometimes it's not like that. Sometimes you have to move away one at a time, two at a time, three at a time, until you find a difference. If there is no difference and you get all the way to the end, then there is no E or Z because it's symmetrical. And symmetrical molecules don't have E or Z because there's no priority groups. So a difference has to be found basically if you're going to have E or Z. So let's name this next one here. So for our numbering, we're going to start on the left. That'll put up bromo at number 3. So we've got 8 carbons. We have oct. It's going to be our prefix. So we're going to have 3 bromo, 6 chloro. We have 2 ethyl groups, 4, 5 diethyl. And then moving down here, because I'm out of room, hyphen. Position of our double bond, it's at number 4. So we're going to have 4-octene. Okay, so that's the part we already know how to do. So now moving on and looking at our priority groups here, we're going to do what we did last time. We're going to break our double bond in half. And then we're going to imagine we split it and we start right here. That's our starting point where that purple dot is on the left. We're only looking on the left-hand side of our break. So when we move away from our purple dot, what do we come to first? We come to first, if we go down from the dot, right here, we come to a carbon. If we go up from the purple dot, what's right here? Another carbon. So at first, we don't have a tiebreaker. Both positions one away from the double bond on the left-hand side, we have carbon versus carbon. No tiebreaker there. So when this happens, you just keep going one atom away at a time until you break the tie. So notice now though, once you move more than one away, there's some decisions to be made, because off of my lower carbon, I can go to a couple things. What is coming off of here? Well, there's a hydrogen that's not shown, so I could go to carbon up here, I could go to the hydrogen down here, or I could go to the bromo. You want to pick the one out of the 3 that is the highest priority. So I'm not going to pick carbon, I'm not going to pick hydrogen because those are lower. I'm going to pick bromo. So we have bromo versus, where can I go on my red carbon on the top? I can go to a hydrogen here, or another carbon on the end there. So out of the three, between hydrogen, and carbon, carbon's my next highest priority. So we're still just on the left side, and so we had to choose between our groups now. What's going to be the high priority group? What's going to be the low priority group? Because bromo won the tie over carbon, that makes this whole thing coming off here our high priority group. And the other ethyl group pointed up would be the low priority group. I'm not going to circle it because it's already getting a little messy. So now on the right hand side of the dark green line, we're going to do the exact same thing. So starting right here, we don't count that one at C5, but moving away from it, if we go down from there, first thing we come to is a carbon. If we go up from that spot, the first thing we come to here is a carbon. So once again on this side, the first thing that happens when we move away is carbon versus carbon. So that doesn't break our tie. So we keep moving. On the bottom, after carbon, a couple things we could choose to go to. We could go to this next carbon, or coming off of this carbon that's not shown is a hydrogen and another hydrogen. Between choosing, I would choose carbon because that's my next highest priority on that branch. So carbon on the bottom versus where can we go on the top? On the top, I can go to carbon after that, or there's a hydrogen coming off of here, or I can go to chloro. So I'm going to choose to go to chloro because that's higher priority than carbon or hydrogen. So now I have carbon versus chloro. Chloro group has a higher atomic number, so that means that this whole group up here pointed up is my high priority group. So looking at this, my two high priority groups, one is up, one is down. They are opposite. So since they are opposite, that means E. So out in front of our name now, we indicate that. We add parentheses and we say 3E and close those parentheses there. We add that stereochemistry out in front, or not 3E. Our double bond lived at number 4 in this one. So 4E. And if you are ever determining priority and you have to, one at a time move away and you have to move through a double bond, the double bond is equivalent to that same number of single bonds. So a CC bond is equivalent to a carbon with two other carbons coming off of it. So we imagine it like that when we're looking at the priority. What's not being shown here is that carbon would be bonded to something like hydrogen there maybe, and that other molecule or atom would still be there, whatever it might be. So CO would be equivalent to carbon bonded to two oxygens, and a triple bond would be equivalent to a carbon with 3 carbons coming off. And so we use this for doing our priority. So a triple bond is equivalent to 3 single bonds. A double bond is equivalent to 2 single bonds. Next, let's wrap this up by doing some examples. We're going to go through some where we determine the name when we're given the structure, and then we'll go through some where we work backwards and we figure out the structure from the name. So starting here, we're going to number from the left. So we've got a lot of groups here. We've got 4 methyl groups listed. So we're going to have 3, 5, 6, 8. That's going to be tetramethyl. And we have another substituent at 4. We have an ethyl group, so really that just looks like this coming off. Remember, ET is just the abbreviation for ethyl. So that is going to come alphabetically before our methyl. So we're going to have a 4-ethyl. And then our position of our double bond is going to be 3. And then we have 9 carbons, so it's going to be none-ene. Okay, so next let's do our stereochemistry now. So looking at our molecule, we have 2 sides that we're going to break this up into. So draw a line down the middle if that helps you. And then starting on the left-hand side here for me, and you'll get better at this as you practice, but notice you have two groups coming off of that red dot I drew. You have an ethyl group and you have a methyl group. What one are you going to run out of carbons on first? It's going to be the methyl group. So that methyl group is going to be lower priority than the ethyl group. So you'll start to see that usually the longer the chain, the more chances that it's going to be higher priority if you're not dealing with something like halogens on it. Because first we come to carbon here, so we have a tie. And then on the top, you could go to hydrogen, hydrogen, or carbon. So I would move on to carbon. And then on the bottom, I can go to only hydrogen, hydrogen, or hydrogen. So it ends up becoming a tie of carbon versus hydrogen, with carbon winning for the top. So right here, that's going to be our high priority group, the ethyl group over the methyl group. And then on the bottom here, or on the right-hand side, I mean, we have our carbon right here, a little bit of a darker red color. And then coming off of that carbon, so we look at one atom at a time, we have carbon, and then carbon here. And then that doesn't break our tie, so we got to keep moving on. On the top one, we could go to hydrogen, hydrogen, or carbon. Well, we would go to carbon because that's higher priority than hydrogen. And then on the bottom one, we could go to carbon or carbon here. So if we were to make a list of what's coming off of the top ethyl group, what's coming off of that top ethyl group after we know the first thing we came to was carbon, and then we came to a carbon or a hydrogen or hydrogen. This is on the top one on the right hand side. And then if we consider the bottom carbon, what did we come to? Off of the bottom carbon, we came to either a carbon or a carbon, and I didn't even write the last thing in there that you could come to. What's coming off of here that's not shown? A hydrogen. So you could come to a carbon on right here, a carbon here, or a hydrogen there. So you could come to carbon, carbon, or hydrogen. So you can actually use this to break your tie now, because the top carbon that we first came to, the very first one, has CHH, whereas the bottom carbon, the very first one we came to, has CCH. So these two tie, but the next two don't. Carbon wins over hydrogen. And then the last two would have been hydrogen, hydrogen. But this guy right there breaks the tie because we had a carbon trumping a hydrogen there. So the larger bottom chain down here becomes the high priority. So it's this whole mess, all of that group sticking off there. That's the high priority group. And so in this example, they're on opposite faces again. And so that's an E. So out front, we're going to add, our position was 3 for our double bond. We're going to add 3E out front here for opposite sides for the high priority groups. Okay, this is a great example because here we have 2 double bonds, and so we have to do 2 separate stereochemistry determinations. So we just do them one at a time like we would for anything else. I'm going to start numbering from the right because that's going to give my double bonds the lowest number possible. And so our name, we're going to have 6 bromo, 4 chloro, and then our double bonds live at positions 2 and 4, so 2, 4, 7 carbons in our chain. We're going to have hept, and then we have to finish this off a little differently because we have 2 double bonds. We call it a diene. So I changed color there just to remind you that the suffix changes a little bit when you have multiple double bonds. So now out in front, we're going to add this part of it. We're going to have 2 E or Z and then 4 E or Z. So we got to figure out what we plug in to that part right there. So let's start on the right hand side. We're going to break our double bond in half. Looking on the right hand side right here, what's coming off of here that's not written? It's just a hydrogen. So we have carbon versus hydrogen. Carbon's going to be the higher priority, so the methyl group wins. And then on the opposite side of our double bond at number 3, what do we have coming off down here? A hydrogen. So we have hydrogen there, That's not going to be high priority. That's the lowest priority, atomic number 1. Moving away from there, at number 4, we come to a carbon. So that makes this whole group right here higher priority. So for this first one, our high priority groups are on opposite sides. So this one right here is going to be E. So we can plug that in out front. We have 2E. Now let's kind of clear some of this away a little bit so we can look at our next double bond. So for our next double bond, we want to start one at a time, moving away from that. So we're going to put our line down it, and then you choose whether you want to start on the left or the right. So make your marker one at a time, move one atom away. If you go up, you come to a chloro. If you go down, you come to a carbon. Chloro is higher atomic number than carbon, so that's higher priority. And then on the bottom, on the other side, coming off of 5, you have a hydrogen there. That's pretty low priority, lowest it can be. So the other thing you would come to next right here would be a carbon at position 6. So you got carbon versus hydrogen. So carbon's higher priority. That makes this whole group right here, the high priority group, pointed up. In this scenario, finally, we have 2 high priority groups on the same side. Since they're on the same side, notice in this case they're both pointed up. They could both be pointed down on some molecules and still be on the same side. So this is an example of Z stereochemistry. So we write 4Z. We also previously learned how to name ring structures, and I wanted to throw this example in here because we actually do not use E or Z for rings. So naming the ring, we kind of follow the same rules that you would have learned when we did just cycloalkanes, giving your substituents the lowest numbers, if you have to use alphabetical order, if you can. But the only difference is we give the double bond the lowest number possible as well. So for numbering something like this, I want to number through the double bond. There's no reason my double bond should not be at position 1 in a ring. And because of that, sometimes it's not even listed. Like people don't even write 1 because it's just assumed to be at position 1. But how the numbering would go is I would start at the isopropyl, and then would I go left or would I go right around the ring? If I go this way, notice I'm not numbering through the ring. My double bond's at 1 and 5, so that's not going to be right. I'm going to number to the left direction. So 1, 2, 3, 4, 5. So this is a 5 carbon ring, so it's going to be cyclo, and then pent for 5, cyclo for ring, pent for 5. We changed the ane to ene. And our substituents are at 3 we have an ethyl, 1 we have an isopropyl. And then some people will just write cyclopentene. It's assumed that in between here, the position of the double bond is number 1. If you wish to write, so same thing right here, 3 ethyl, 1 isopropyl, hyphen 1 cyclopentene, you can. You can say number 1 like that and put it with hyphens there. But it's just assumed to be at position number 1 because it's in a ring. We have to give the double bond the lowest priority, so where else would it be? And just a reminder also, this PRI with a superscript there, that's just the abbreviation for this common group, which is our isopropyl group. Just like ET is the abbreviation for an ethyl group coming off. So you also want to know those common abbreviations because they're used all over the place. So when going the other way, when you are given a name and you want to draw a structure, it's a little easier because you don't have to figure it out, but you do have to see if what you drew is the correct stereochemistry. So what I suggest you do is you just throw something down, you draw it down like how you normally would, whatever your method is, and then you check it. Did you make something E or did you make something Z? And if it matches, good, you're done, if it's what you need it to be. If it's not, then you got to move some groups around after. So let me show you what I mean. We got 4 undecane. That should say undecene, E-N-E. So change that in your notes. So undecene is going to have 11 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then at position 4, in between 4 and 5, that's where our double bond is. We're going to throw our substituents on there. So at 4, we have a bromo. 3, we have a chloro. 5, we have an ethyl. And then 7, we also have another bromo. So place all our substituents. Okay, now we know we want our stereochemistry to be Z. So we want our high priority groups to be on the same side. Now, I don't know if they are yet. I have to check them out after I get done with this part. So break your double bond in half, your imaginary line, and start on one side. So right here on this side, you got carbon, carbon, and then both of those you would come to 2 hydrogens, and then another carbon and carbon, and then the ethyl group 1, that's shorter, we ran out, we would only come to either hydrogen, hydrogen, or hydrogen, and on the next one we can come to a bromo. So that means that this whole big group that contains that bromo is the high priority group. Basically, the high priority group is pointing up. On the other side of the double bond, so now we got to look at the other side. This one's really easy. We first go up, we come to bromo, we go down, we come to carbon. Bromo is higher priority than carbon. So for this one, we got lucky. Our 2 high priority groups are both on the same side. So what we drew was already Z. So that's good. It matches what we wanted to draw for our molecule. So this would be the correct structure. I don't have to modify where any groups are to change the stereochemistry. Next, let's draw a cyclic alkene. We got 4-sec-butyl, 4-isopropyl, cycloheptene. And if you're wondering why sec-butyl is before isopropyl, it's because it goes by B for the alphabetical order. So cycloheptene means we have 7 carbons in the ring. It's a little weird to draw. I'll try to draw it without messing up. So we got 1, 2, 3, 4, 5, 6, 7. And this one does say 1 cycloheptene. Even if it didn't and it just said cycloheptene, we still would assume that between position 1 and 2 is where our double bond is. And then coming off of position 4, we can use the abbreviations for these, or we could draw them out. We can write BU superscript S for sec-butyl, and we can write PR superscript I for isopropyl. Just a reminder, sec-butyl looks like this. It's 4 carbons, and on that subbranch, carbon number 2, or the secondary carbon, is what would be attaches back to the main parent chain. All right, let's finish this nomenclature lecture up with one more example. We got 3Z, 7E, 2,5-dichloro, 3-ethyl, 1,3,7 dodecatriene. So you might notice right off the bat that there's 2 stereochemistries given here, but we have a triene. We have 3 double bonds. And that's because if you have a double bond that is terminal or at position number 1, it doesn't have any E or Z because all that's coming off of the end there is 2 hydrogens. And there's no tie to break between 2 hydrogens coming off the end there. And so there's no E or Z. If there's no winner between the priority, there is not an E or Z designation. So let's first, remember, just throw something down on paper and then we check if our E's and Z's match and we change what we have to. So we're going to draw 12 carbons in our chain. We got a dodec. So 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. Sorry, I always have to check after I draw it to make sure I drew the right number because it's easy to mess up. And then in positions 1, 3, and 7, we're going to have 1, 3, 5, 6, 7, and then between 7 and 8, that's our next double bond. Throw our substituents on there. 2, we have a chloro. 3, 4, 5, we have a chloro group. At position number 3, we have an ethyl group. 1, 2, 3, we got an ethyl group there. All right, so we have all of our substituents on there. So we don't have to check number 1. Number 1 has no E or Z, so here, let's add these in. There's a hydrogen there and a hydrogen there to fill in the 4 bonds for carbon. So there's no difference between those two. So there's a tie, so no E or Z coming right there. But looking at our double bond at position number 3, there's going to be a priority difference there, and we want Z. We want 3 to be Z. We don't know if it is yet, so that's why we have to check. So starting right here, it's our first one on the left. And I think as you do enough of these, you'll see that it does not take as long as this lecture has been taking. You can quickly learn to look at a molecule and you'll be able to predict if it's E or Z with a little practice. But first you come to carbon here. Next you come to carbon here. Okay, after that first one, we have to keep going because it did not break our tie for us. On the bottom one, you've got hydrogen, hydrogen, carbon. On the top one, you've got chloro, and then you got carbon double bonded. So that's like having, if I just draw this little portion of it right here, what it really you want to think about it like is you've got carbon with a chloro, and then carbon for the double bond part. This is where if you have a double bond, it comes like 2 singles, carbon, carbon. So that's what we draw the double bond as, 2 single carbons coming off. So on that top carbon, it's like you have chlorocarbon, carbon. So chlorocarbon, carbon is going to trump carbon, hydrogen, hydrogen on the bottom. That means that this right here is our high priority group. And then on the other side, we've got, coming off of this carbon, we have a hydrogen, that's a sign, and then down we have a carbon. So hydrogen is lower atomic number, it's lower priority. So that's our high priority group. Okay, this is a situation where, okay, now our high priority groups are on opposite sides. One is going up on that side of the double bond, and the other one is going down. So since they're opposite, this is not Z, this is E. So what I do when I come to a situation like this is I flip 2 of my groups. I can either flip 2 on the right or 2 on the left. So I picked the smaller ones. Notice on the right, I circled a really big group. That's going to be harder for me to redraw. So I'm going to redraw part of this molecule, starting with the double bond. And so here's where my double bond is. Here's where my chloro would be. Here's where my other double bond would be. Ooh, that got a little messy at the end. It's a little squiggly now, but that's okay. And so I'm going to flip where my position of my 2 groups are. And it's a little hard to see, but we had an ethyl group pointed down, and then we had a chloro-substituted group pointed up. So instead I'm going to put my ethyl group coming off of here. So there's my ethyl now, put it up. And then my other group, which is a carbon there, and then there's that terminal double bond, and then there's that other chloro group. That's pointed down now. See, I flipped the position of those 2 groups. And when you do that, now this double bond right here becomes Z. It was E the other way, it's Z this way now. And you can even see that. You can see that the 2 high priority groups are both pointed down. One here, one here. So that's good. And now we check our next one. We check our next double bond. So break it in half. This one's a quick check. We got hydrogen here, hydrogen here. So if we start on the right-hand side, this carbon chain is going to be high priority because you got carbon versus hydrogen. Carbon wins. And then on this other side here, you've got carbon or you've got hydrogen. And so then this whole chain wins. So you got your 2 high priority groups. In this case, they're on opposite sides, one up, one down. So that's E. And that's what we wanted. We wanted E for double bond 7. So before I marked all this up, this molecule right here was the correct way of drawing it. So let me just draw it neat up here so you can see what the final structure was supposed to be. I think I got that. Let me check here. We have the ethyl, double bond here, double bond there, chloro group there. And when you redraw something, this is a good kind of point to make. Make sure that you are rechecking that you're putting your double bonds and your substituents back on there and you're putting them back in the right spot. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I got that. So my double bonds are still at 1, 3, 7. Now I have the correct stereochemistry for 3 being Z, 7 being E. And that would be my final answer for this alkene.